So the lesson today is on transformations, lesson 5, stretches about the x or y axis, part 1. Stretches now, so we're not doing translations, we're not doing reflections, these are stretches. So what exactly does that mean? Well, basically, if you are at, say, if you're doing a stretch from the x-axis and you're 1 above the x-axis and you happen to do a stretch or a multiplier of 2, you'll end up stretching up to a height of 2. Say you start at a height of 2 down here in the graph, and you use a multiplier of 3, you'll go from 2 up to 6, up to a height of 6, and end up here. That's what's meant by a stretch about the y-axis, and the same goes for the x-axis, and the same goes for the y-axis. So let's take a look at some of these examples. We have a graph, and this graph here is, or it says the graph of y equals f of x, which is the square root of 4 minus x squared, is shown. Write the equation which represents y equals 3 of f of x. So that simply means a multiplier out front. So this one here, this graph here, this semicircle is actually the original. So let me write the y equals f of x here. That's the original one. Now this is the function which has been multiplied by 3 times. In other words, if we think about it, whatever y was before, this has been multiplied by 3. And here's the new equation, and here's the new graph. So whatever height it was before, for example 2, it's now been multiplied by 3 and it ends up at 6. If the original graph was at, say, 1, should be up at 3. So there's 3. It was originally at a height of 1. So you're really just stretching as if we have a rubber band, and any point on the x-axis, such as here and here, are points that don't change. And I've forgotten the terminology there, we did it a couple of lessons ago. So these do not change the position. In fact, everything stretches from here and gets pulled up. Okay. Using a graphing calculator, sketch this on your grid. Well, so you're sketching this guy here, and you can try it out. Notice it's only the positive square root, so you only get the semicircle here. And multiplying it by 3, you'll get this. So parabola, it's only a partial parabola, it doesn't extend below the x-axis. Describe how the number 3 affects the general stretch. Well, it's just a vertical stretch about the x-axis. The x-intercepts of the graph, well, there's no change. No effects on them. How about the y-intercept? Well, yes, the y-intercept was here originally. It's been stretched or multiplied by 3. Part 2. Write an equation that represents y equals a half f of x. Well, that would be a half of the root of 4 minus x squared. So what does this half do? Well, it multiplies all the y values, previous y values, by a half. So guess what? Your original graph shrinks in its y values. So it's, let's see what it has here. In part C, describe how the number 1/2 in this formula affects the general sketch. Well, it's a vertical stretch by a factor of a half. The x-intercepts again do not change, and the y-intercept of the original graph is multiplied by a half. It goes from 2 down to 1. Complete the following statement. Compared to the graph of y equals f of x, the graph of y equals a, which is just the multiplier, times f of x, results in a vertical stretch about the x-axis by a factor of whatever a happens to be. Note, if we replace y with 1 divided by a times y, then y equals f of x becomes 1 over a y equaling f of x, which is equivalent to, sorry, I haven't chosen the pen here. I will get this right in a sec. Yeah, which is equivalent to what we've just been talking about. So the a could end up on this side. Typically it is on this side, but occasionally you'll see it on the other side here. So these two equations mean the same thing. Well, the replacement, you can see what the replacement terminology is. Y has gone from the original up here. Well, it's gone from, I'll write it down here, y equaling f of x to 1 over a y. So this down here is the replacement terminology for what's happening. Okay, comparing graphs of y equals f of x and y equals f of bx, where b is greater than 0. So notice here this multiplier b is inside the function, and it's inside the function multiplying the x. The last examples we just looked at had an a multiplier outside the function. This is a b inside the function. Does two completely opposite things in a sense. The a really affects how the graph looks height-wise. It affects the y values, so it's a stretch from the x-axis. Stretching is if it's tied down to the x-axis and stretching up or down in the y direction. But the b value actually is a stretch along the y-axis. So as if you can see what's happening to the original graph here. This new graph is actually being compressed. The intransient point here, the one that's not moving, is actually on the y-axis, does not move. So the example they're giving us here again is the same graph for the same semicircle here, and write an equation which represents y equals f of 4x. So what does that mean? It means x has been replaced by 4x. So here, this x gets replaced by 4x. Fair enough. We can multiply that out and we'll get negative 16x squared. If we use a calculator and put this into our calculators, we'll find we get a new graph like this. A lot smaller, looks like it's being compressed into the y-axis. This is actually a stretch by a factor of a quarter. Describe how the number 4 in this new function affects the general sketch. Well, it's a horizontal stretch, so it's gone in, it's being compressed in a sense, or a horizontal stretch about the y-axis by a factor of a quarter. The x-intercepts have also been multiplied by a quarter. So instead of being at 2 and negative 2, they're now at negative a half and a half here. The y-intercept, notice, has not changed. So part 2 of this, instead of using like 4x here, is using 1/3 to show that if it's a fraction less than 1, still positive though, what it does, if you can see, it goes in here and replaces the x and gets squared, we get negative 1/9 x squared. What it really does is this third actually ends up being a stretch by about the y-axis by a factor of 3. This point at 2 goes to 6. So we're now at negative 6, and this point at 2 goes out to positive 6. Negative 2, negative 6, 2 goes to 6. Again, this point here on the y-axis does not change its position. So complete the following statement using the results of part 1 and 2. Compared to the graph of y equals f of x, the graph of y equals f of bx, this number is multiplying the x within the function. It results in a horizontal stretch about the y-axis by a factor of 1 over b. So it does the opposite to what you'd expect. 1/3 actually stretches it by a factor of 3. If this had been a 3, it would have, in a sense, compressed it. It would have been a stretch by a factor of 1/3. So if we replace x with bx, then this function becomes this function. So the replacement in this example is just x goes to bx. Replacement terminology. Alright, comparing the graphs of f of x and y equals a f of x, where a is less than 0. So if it's less than 0, means that a is negative. So this multiplier out here is negative. What will that do? Well, not only will it be a stretch, but it should also be a reflection. Remember, if this is a negative value, it's a reflection in the x-axis. So let's consider this graph here. It's a cubic function, cubic functions, and it's a positive x cubed. So that would start up here and have 1, 2 bends in it and come down here. So that's f of x here. Now, we'll write an equation that represents negative 3 f of x. So here's an equation. If you multiply the original one by negative 3, you get this. What does that look like? Well, you can use your graphing calculator, but this is really all the y values are getting multiplied by 3 and reflection in the x-axis. So let's reflect in the x-axis first. Let's take a couple of points that really mean something. For example, this one here, and let's say something, since we know it's a multiplication, let's take something with a height, say, yeah, maybe a height of 2. So around about here. Height of 2 over here, perhaps. Now it's going to be a stretch centered at the x-axis. So this point should not change in the original function, and it doesn't. At least it doesn't seem to. Okay, and then coming over here, we have another height, say at, well actually this, if I'm looking at the scale, I'm noticing it's 4. Every box is 2. So this has a height of 4. So does this. This is a height of negative 4. So now when we do the reflection, the negative here, it's a reflection in the x-axis, and but we also have an expansion in the x-axis. So this point at positive 4 will go down to negative 4, but it gets multiplied by 3. So we actually go down to negative 12, which is actually down here. So we actually end up there. So they change colors probably, be a better idea. So yeah, we end up down here. What about this point? This was at negative 4. First of all, do a reflection in the x-axis. We end up here. So yes, this gets reflected in the x-axis, ends up here, but then we get a multiplication by 3, so instead of being at 4, a height of 4, it actually ends up at a height of 12. Just got to keep in mind that two things are going on. Next point here, reflection in the x-axis doesn't do anything, and it's at a height of 0, so multiplying by 3 doesn't do anything, so it stays there. This point is at 8, so we go down to basically negative 8 in the reflection in the x-axis, which then gets multiplied by 3, ending up at 24. Our next point in the curve is at positive 4, gets reflected to negative 4, and then multiplied to negative 12. Last point that we chose was at negative 4, gets transferred over to positive 4, and then multiplied to end up at positive 12. So you can see how we can sketch this new graph with the red dots on it. You can verify that with your graphing calculator and describe how the number negative 3 affects the original function. Well, it is a reflection in the x-axis. Okay, that's that, negative. And the 3 means it's a stretch from the a stretch from the x-axis by a factor of 3. So here's the answer here. Notice that this has been written in already, and it doesn't seem to matter in this case if you get the reflection followed by the vertical stretch about the x-axis, or the stretch happens first. And we'll talk more about that later. In this case, the order does not matter, but don't worry about that right now. The x-intercepts of the graph, well, if you recall the graph just above, the x-intercepts did not change. However, any y-intercepts, whatever height they were at, have now been multiplied by negative 3. They've been reflected and multiplied by 3. So compared to the original graph, this graph, when a is negative, results in a vertical stretch about x-axis by a factor of modulus a, or absolute value of a. So it also happens together with a reflection in the x-axis. So now it goes on to talk about what if b was actually less than 0. How would that affect things? Well, again, we can see that b has to do with a reflection in the y-axis, and if it's negative, because it's multiplying the x, sorry, I think I'm getting my terminology mixed up. B, the value of b is has got to do with a stretch about the so stretch about the y-axis, and if it's by negative, if b is negative, you will get a reflection in the y-axis also. So let's look at the equation down here. We've got f of negative a third of x. So this is the original function here, and replacing negative a third wherever we see x results in this equation here or this here. This could be graphed using a graphing calculator. Let's see what happens without the calculator. Let's just look at the original graph. This is the original graph here. Y equals f of x. So notice if let's take some points here that we can reflect and stretch. Let's see, take the zeros of the function as well. Perhaps that might help. And also this seems to be an intransient point, it doesn't move. Okay, so let's deal with this point here. what will b do? If it's multiplying the x itself, it's basically, we're saying it's a horizontal stretch because it's affecting x, the x values. So a horizontal stretch. It's about the y-axis. So if b is less than 0, now here it's negative a third. It's not the fact that it's a third, it's the fact that it's negative that makes b less than 0, obviously. But we're using a third. So in fact, this is going to be an expansion. It's the opposite of what, remember when the number is beside the variable, it's opposite to what you'd expect. Now that was a bit like where y equals f of x goes to y minus 1 equaling f of x. Now this is actually opposite to what we'd think, because when we bring this to the other side, we get y equals f of x plus 1. We're raising this graph up, the original graph up by 1. But when this number is beside the y, it sort of looks the opposite. Okay, negative 1, but it's actually a translation up by 1. Well, the same sort of thing here happens. A multiplier right beside the x does opposite to what you would think. It's actually a stretch by a factor of 3, not a third. So I'm just telling that to myself so I can understand what's happening to this point here. We're going to get a stretch about the y-axis by a factor of 3. So where would we end up? Typically, this point is at here, and it's at, I'd say, 1 and almost 3/4. So ends up at 9/4. 1 over 9/4, that's 2 1/4. Basically, it should end up out about here. So I'll just put a little x. I'm not sure if that's quite right. Let me just think about that for a moment. Okay, so yes, this point here goes to this new point here, represented by an x. But as well as the stretch because of b, because of the stretch by a factor of 3, we're also going to get a reflection. This negative is going to be a reflection in the y-axis. It's affecting, it looks like it's with, this negative is with x, but as we know from before, reflections like this, if it's negative, if x goes to negative x, it's a reflection in the y-axis. So this actually comes over to about here. So again, that's about almost, I think this graph's not quite drawn accurately. Alright, let's take another point. So this one, first of all, we get a horizontal stretch by the y-axis, so that won't move. And then again, if we reflect in the y-axis, also that won't move, so that stays where it is. I'm just going to change colors. So we've got this new point here, and then this new point that hasn't moved. So we dealt with that one. Let's see what happens here. This is at -2 with a stretch by a factor of 3, should go out to 6, but then gets reflected way over to positive 6. So that's that one, and that one, that one. Now let's move to here. We're at positive 1. We get a stretch by 3, ends up here, but then a reflection chases it over to -3. So we've done that one. Now this one, it's at x value of 2, stretches it by a factor of 3 to 6, but then gets reflected way over to the other side to here. Okay, and then this one, it's at 3, ends up at 9, gets reflected over to -9. And we could choose another point up here, say with an x value of 3.5. 3.5 times 3, 10.5. So this would end up way over here somewhere at 10.5. It's not quite accurate on this side. But anyway, you can see how this new sketch would end up like this. So describing how the number negative 1/3 in this function affects the general sketch. Well, as we mentioned before, it's a horizontal stretch about the y-axis by a factor of 3. And it's also a reflection because it's negative in the y-axis. The x-intercepts of the graph, how do they change? Well, the x-intercepts would be stretched by a factor of, well, 3 and the reflection as well. So it's multiplied basically by negative 3. If I was sitting on the x-axis at 2, it would go out to 6 and then get reflected over to negative 6. So 2 times negative 3 is negative 6. That's what's happening. The y-intercept, no change. Completing the following statement, I'll let you read that yourself and pause the video before I move on. So in mathematics, we use the word stretch to represent both an expansion or a compression. In this course, we want to consider stretches about the x and the y-axis. In the table below, the graph of y equals f of x and the graph of y equals a f of x or y equals f bx is given. Fill in the blanks. So this graph will be stretched vertically by a factor of a about the x-axis if a is between 0 and 1. In other words, if it's a positive fraction less than 1. If a is greater than 1, then the graph is stretched vertically by a factor of a again about the x-axis still. If a happens to be negative, then the graph will be reflected in the x-axis and is stretched vertically also about the x-axis. So here's some examples of what would happen. Thick line is the new graph. So you might want to pause and just jot this down. Dealing with b, b is multiplying the x value. If b is a positive fraction less than 1, the original graph will be stretched horizontally by a factor of 1 over b. So if b was, say, 1/2, it's going to be stretched by a factor of 2 about the y-axis. And here's an example. If b is greater than 1, again it's a horizontal stretch by a factor of 1 over b, still about the y-axis. So if b happened to be 3, then it would be 1/3. So in a sense it would be a compression. Okay. So here the new line is squished into the y-axis on both sides. If b is negative, then you are reflected also in the y-axis and stretched horizontally about the y-axis. Here's an example here. Okay, so y equals a f of x is equivalent to bringing the a to the other side and having it as 1 over a times y equaling f of x. You can see again, as I talked about the x value just above, when the multiplier is beside the variable, it does opposite to what you think. This would be, if a was, say, 3, so you'd have 1/3 here, this would be an expansion by 3. So if you have a 3 here, it's an expansion, sorry, if you have a, 3 here, it's an expansion by 3. Here it's not directly beside the variable y, it's affecting the height. It's actually a stretch about the x-axis, affecting the heights of y. So when it's on this side, it does what it looks like it's doing. When this is a 3, then it's a expansion by 3. When it's on the other side, it's 1 over 3, right beside the variable. It does opposite to what you'd expect. Okay, I'll let you just read through here and understand what all this means, and I'll record a second video, second part to this, so that we can break this video session into 2 parts.